Have you ever wondered if the next generation of body armor, or even a robot that helps care for your grandparents, could owe its existence to a grain of rice? What if one of humanity's oldest crops held the secret to creating materials that can instantly change their behavior depending on what's happening around them? Imagine touching something that's as soft as a sponge while you move slowly, but becomes almost rock solid the instant it's struck. It sounds like science fiction. But researchers are now developing smart materials inspired by rice that automatically adapt to different kinds of force, without batteries, computers, or motors. And this breakthrough may be just the beginning, because scientists aren't simply creating stronger materials anymore. They're creating materials that can think in their own mechanical way. Today, we're exploring how rice-inspired engineering is changing the future of robotics, protective equipment, medicine, transportation, and perhaps even the clothes you'll one day wear. Let's begin. For thousands of years, rice has been one of civilization's most important crops. It's fed billions of people. It's shaped cultures. It's built economies. But now, scientists have started looking at rice from an entirely different perspective, not as food, as engineering. The secret isn't the rice itself. It's the microscopic structure hidden inside. Nature rarely wastes effort. Over millions of years, biological structures have evolved to balance competing goals: strength, flexibility, lightness, efficiency. When engineers look closely at certain rice-based cellular structures and packing geometries, they discovered something remarkable: tiny arrangements capable of distributing force in surprisingly intelligent ways. Instead of resisting every force equally, they responded differently depending on how they were loaded. That discovery inspired researchers to recreate similar architectures using advanced manufacturing techniques. The result wasn't simply another lightweight material. It became something entirely new, a programmable mechanical material. To understand why this matters, think about walking across a trampoline. If you step gently, it bends comfortably. Now imagine jumping onto solid concrete. The experience couldn't be more different. Traditional materials usually behave consistently. Steel remains steel. Plastic remains plastic. Foam remains foam. Their properties are mostly fixed. But smart mechanical materials change their response automatically. Move slowly, they're flexible. Strike them quickly, they stiffen almost instantly. No electronics, no sensors, no software. The intelligence is built directly into the structure itself. Scientists sometimes call this mechanical intelligence. The material geometry performs the decision-making. How does this happen? Imagine hundreds of tiny interconnected cells, each one shaped carefully, each connected in precise ways. Under gentle pressure, these microscopic structures rotate, slide, compress, and redistribute force smoothly. But under sudden impact, those same movements become impossible. The architecture locks together. Energy spreads rapidly across the network. The entire material stiffens within fractions of a second. It's similar to how a crowd behaves. People walking calmly can move freely, but during an emergency, everyone presses together. Movement becomes restricted. The group suddenly behaves very differently. The same people, different conditions. That's exactly what's happening inside these new materials. This ability opens astonishing possibilities. Take protective sports equipment. Helmets today involve compromise. Too soft, and they don't absorb major impacts. Too hard, and they're uncomfortable during normal use. Now imagine a helmet that's soft while you're wearing it. Comfortable, lightweight, breathable. But the instant your head experiences a collision, it becomes dramatically stiffer. Protecting your brain exactly when it matters most. Then, once the impact is over, it relaxes again. No switches, no batteries, no activation required. Just physics. The same concept could revolutionize body armor. Current armor often sacrifices comfort for protection. Soldiers, police officers, emergency responders, construction workers, athletes, they all carry heavy protective equipment. But future armor may remain flexible during normal movement, allowing natural motion, then instantly harden against impacts. Imagine clothing that protects only when protection is actually needed. The difference could reduce fatigue while improving safety. Perhaps even more exciting, soft robotics. Traditional robots rely on rigid metal frames. They're powerful, they're precise, but they're also dangerous around humans. A rigid robotic arm moving unexpectedly can cause serious injuries. Soft robots solve part of that problem. Built from flexible materials, they're much safer. But softness introduces another challenge. They struggle to lift heavy objects. They bend too easily. Now imagine robotic muscles made from smart adaptive materials. Normally soft, gentle enough to handle delicate fruit or assist elderly patients. But when lifting something heavy, their structure stiffens automatically, without complex control systems. The material itself provides the adjustment that dramatically simplifies robot design. Medical technology could benefit as well. Imagine surgical instruments, catheters navigating blood vessels, medical implants, wearable braces. Each could remain flexible while being positioned, then become more rigid exactly where support is needed. Researchers are investigating adaptive medical materials capable of responding naturally to the body's movements. The goal is improving comfort, reducing injury, and allowing devices to work more harmoniously with living tissue. Transportation is another frontier. Cars already contain crumple zones, but those zones don't adapt. They're designed for average conditions. Future adaptive structures might respond differently depending on collision speed. A low-speed bump, a high-speed crash, different mechanical responses. The material itself could optimize energy absorption. Engineers are also exploring lightweight aerospace structures capable of adapting to changing aerodynamic forces. Imagine aircraft components becoming temporarily stiffer during turbulence, then relaxing once conditions improve. What's fascinating is that this Rice-inspired breakthrough isn't happening alone. We're entering an entirely new era of material science. Researchers worldwide are developing substances that no previous generation could have imagined. Materials that heal themselves, materials that remember shapes, materials that harvest energy, materials that clean themselves, materials that sense damage before humans notice. Each breakthrough builds upon another. Together, they're transforming engineering itself. Consider self-healing materials. Tiny capsules hidden inside release repair chemicals when cracks form. Instead of damage spreading, the material begins repairing itself. Scientists have even developed polymers capable of reconnecting broken molecular bonds. Imagine bridges lasting decades longer, phone screens healing scratches, spacecraft repairing microscopic impacts from space debris. The implications are enormous. Then there are shape memory alloys. These remarkable metals seem almost alive. Twist them, bend them, deform them, apply heat, and they return to their original shape. It's like watching metal remember its past. These materials already appear in medical devices, aircraft systems, and industrial machinery. Future generations may become even more responsive. Researchers are also creating programmable metamaterials. Unlike ordinary materials, their unusual properties come from geometry rather than chemistry. Tiny repeating structures manipulate force, sound, heat, even light. Some can become extraordinarily stiff while remaining incredibly light. Others bend in unexpected directions. Some exhibit negative Poisson behavior. Stretch them, and instead of getting thinner, they expand sideways. It's completely counterintuitive, yet entirely real. Energy harvesting materials represent another revolution. Imagine roads generating electricity from passing vehicles, shoes charging wearable electronics while you walk, buildings converting tiny vibrations into usable power. Scientists are designing piezoelectric systems capable of transforming mechanical movement into electrical energy. Tiny amounts individually, but enormous potential when scaled. Another exciting direction involves responsive textiles. Today's smart clothing often depends on electronics. Tomorrow's fabrics may respond mechanically, opening microscopic pores as body temperature rises, changing insulation automatically, providing support during physical activity. relaxing during rest. Your clothing could adapt continuously without requiring charging. Even construction materials are becoming smarter. Researchers are developing concrete capable of monitoring its own structural health. Other teams are embedding sensing capabilities directly into building materials. Future bridges may report tiny fractures long before failure becomes dangerous. Entire buildings could continuously monitor themselves, not because computers are everywhere, but because the materials themselves participate in sensing. Perhaps the biggest shift is philosophical. For centuries, engineering focused on stronger, harder, thicker, heavier. If something failed, we added more material. Today, scientists ask entirely different questions. Can a material adapt? Can it respond? Can its structure perform useful functions? Instead of fighting nature, researchers increasingly learn from it. Bones, wood, spider silk, lotus leaves, shark skin, butterfly wings. Now, rice. Nature has spent billions of years solving engineering problems. Humanity is finally learning to pay attention. Artificial intelligence is accelerating this process. Instead of testing thousands of material designs manually, AI models can evaluate millions of microscopic architectures, searching for combinations humans might never imagine. Researchers simulate countless structures digitally, predicting which geometries deliver desired mechanical behaviors. This dramatically shortens development time. The partnership between AI, advanced manufacturing, and bio-inspired design may define the next generation of engineering. Of course, challenges remain. Manufacturing complex microscopic architectures at industrial scale isn't easy. Costs must decrease. Durability must improve. Long-term performance requires extensive testing. Materials behaving perfectly in laboratories must survive years of real-world use. Engineers also need consistent manufacturing methods. Tiny imperfections can change behavior. Scaling scientific breakthroughs into affordable consumer products always takes time. But history shows what happens when entirely new classes of materials emerge. Steel transformed civilization. Plastics reshaped manufacturing. Carbon fiber changed aerospace. Semiconductors created the digital age. Adaptive mechanical materials may become another defining chapter, not replacing existing materials, but giving engineers capabilities they've never possessed before. Materials that don't simply exist, materials that participate, materials that respond, materials that adapt. It's astonishing to think one of the oldest agricultural plants on Earth helped inspire one of the newest frontiers in engineering. Sometimes, the future doesn't begin with exotic substances found on distant planets. Sometimes,